Okay, here's the beam system. We've got a piece of shelf standard here, 2 feet long, a couple of 1-foot straps mounted to that, and a bunch of magnets and stuff on it. There was a domino, but I'm not going to put the domino on, it doesn't stick. I'll dump it. Okay, so if I get this thing turning, well, each magnet has some distance from the axis. We can figure out how many radians per second of angular velocity we've got, maybe by observing, counting. It's slowing down a little bit. We already know how to calculate the acceleration. We've observed that. So we can easily observe that, get the acceleration and all that stuff, and pretty much understand the motion of this thing really well. Okay? Now I've got a rubber band hanging on this thing. Why have I got a rubber band hanging? Well, because I can grab it and look at that. Okay? Now, is it going the same speed it was? Could it be going faster? Well, that depends. If I grabbed this thing and held the rubber band stationary, it can't be going faster afterwards. If, consciously or unconsciously, I pulled back on the rubber band a little bit when I stopped it, that would have another effect. And look at this. You can have the thing going back and forth here, gradually losing energy. There it goes. Okay? Now we know this thing's unbalanced, so it has a natural simple harmonic motion if we just leave it alone. But if we get it moving fast enough, the energy of the rotational motion pretty much overwhelms any energy changes we get as a result of the restoring torque. Okay? And of course I'm not holding it steady, so there are all kinds of uncertainties, but you get the idea. Okay, so that's kind of what we're talking about here. Now, that rubber band off of there. The question that we want to start with, at least as far as what happens to this rubber band, is how much potential energy does that rubber band have? How do we know the potential energy of the rubber band? How do we know then how much energy this rubber band has to release to that system? And then can we measure the motion of that system in such a way that we can account for the potential energy that we lost from the rubber band? Well, we're never going to account for all of it. There's energy being lost. But most of the potential energy of this rubber band will go into that system, and we can make comparisons. The rubber band, of course, is kind of a complicated thing, and energy relationships, their histories, loops and stuff like that we don't want to talk about right now. So for right now, we're going to just treat the rubber band as kind of we're going to treat it as if it's an ideal rubber band, but we're going to notice that it isn't ideal. By ideal, meaning that means the force is conservative. You know what conservative force is?
It always does its best to return to its original shape.
I'm sorry, I don't have the hearing aid in. You said it just fine.
It's a force that tries to restore it to its original shape. Or is that restoring force?
That's a restoring force, but an elastic restoring force and the force exerted by an ideal rubber band would do that sort of thing. In other words, a linear restoring force is conservative. But why is that? Okay, so again, these are things that I have recommended. You just start a page, and you only need about a page of key ideas and key concepts and key definitions. You don't even have to state them fully, as long as maybe on another page you've got full statements that you can refer to and review it periodically, at first every day. After you get them down a little bit, every few days, every week, as long as you keep them in front of your mind, then we get into a situation like this and you can quote those definitions and reason from the definitions. But if we don't have the definitions, we can't do that. So, repeating. and you might go back to the video where I developed this in terms of a system. The change in PE is equal and opposite to the work done by conservative forces. The total net conservative force. Now, I mean, change of potential energy of some system that's acted upon by conservative force. I don't want to put all those words down, but you need to know basically this idea and then the words you need to qualify things so you can apply it precisely. Otherwise, unless you have a lot of experience, you never know whether you're applying it correctly or not. You're just taking a stab in the dark, and a good stab in the dark is worth something. Okay, it can be refined to real understanding. Okay, and hopefully you do that. Okay, so change of potential energy is equal and opposite to the work done by conservative forces. What are conservative forces? Path-independent forces. The restoring force, which you mentioned, the linear restoring force, is path-independent. If you reverse direction, the frictional force reverses direction. Okay? So, those are just examples. There's problems you need to work out and so forth to understand how all this works together. Okay? Now, since we're on this topic, I'm going to introduce another because it's just an opportune time. A little off the topic of what we're going to do, but very relevant anyway. I mean, totally relevant to what we're doing. I wasn't going to do it now, but I'm going to do it now. Okay? So, we know that the work done on an interval by a net force is equal to the change in kinetic energy. Okay, well, your net force is typically a combination of conservative and non-conservative forces. For example, if you have a simple harmonic oscillator with this linear restoring force, okay, but it's sliding on a tabletop, it's going to be losing energy to friction, right? Okay, so you have the conservative force. If you have an ideal situation, you have a conservative force and you have a non-conservative force, right? And your net force is the sum of all forces, so your net force can be broken down into conservative and non-conservative parts, okay? Okay, I probably should say F net conservative and F net non-conservative, but that's not really right either, so there's no real good way to label it, so I'm just going to say that, okay? Maybe I should say total, conservative, total, non-conservative. But you get the idea. Well, okay, so can't read that, but it says non-conservative, so I can't read that, but you know what they say. Okay? Okay? Now, a little clarification. This is the net force on the system. So this is the work by the non-conservative force on the system. Okay? And to remind ourselves, I didn't use the subscript here. But whether these forces are acting on the system or whether they're forces exerted by the system. You have Newton's third law, okay? Any force that acts on the system is going to be met by an equal and opposite force. That didn't state that totally right, and we'll worry about some subtleties of that definition later, but you get the idea, okay? So you got to worry about whether force is exerted on the system or by the system. So, as not to worry too much, we have this, okay? So, what's the relationship of the work done on the system by the net force or by the conservative force and change in potential energy?
Potential energy is equal and opposite to the work done by conservative forces. So,
yeah. And I should say, on the system by conservative forces, right? Because if the system exerts a conservative force on something else, you get confusion. Okay, so we'll be a little careful about that. And I probably ought to include that in my definition, but if there are too many words, people start never remembering them because people never even remember the simple words. Okay, I don't know why, because I don't review. Be the 1 in 100 that does it right. Okay, so we have this. So I'll use NC for non-conservative. I don't have to mention conservative because that's part of the definition of potential energy change. Okay? And another way of saying that is now how do I get from this to delta KE and delta PE?
well, the net work is equal to the change in kinetic energy.
Yeah, so instead of delta W net, I use delta KE. And we totally understand where that comes from because we can derive it, right? How do we derive it? I'm not going to put you in the spot, but you know you can get 4 equations of uniformly accelerated motion if you start with the assumption that acceleration is uniform. You can do that either by integration, which you did in the first day, and have no trouble with, You can get a couple equations of motion, a motion for V of t, a motion for x, or an equation for x of t. You can eliminate variables, and you get 4 equations of a uniformly accelerated motion in the case where, of course, acceleration is uniform, okay? One of those equations reads Vf squared equals V naught squared plus 2a delta x, okay? And if you plug A equals F net over m from Newton's second law in for A, this falls out. And you need to know that derivation. Okay? It's almost certain that that derivation or a similar one's going to be on the test. Okay? I think I posted a bunch of things to think about on Monday. So, and I think I just reviewed that this morning. I'm doing a lot of stuff right now. I don't know what I'm thinking. Okay? It could be my fevered imagination, but I'm pretty sure I did that.
No, you did.
I also, I think, no, that was in the other class. I had one out to another class. I did the pre-calculus classes. Okay. Well, this is another form of the work energy theory. Okay? Where you split off this work done by the net force into the change of potential energy and the work done by non-conservative forces. Okay? And this is another one I need you to know. Okay. Probably won't test you on it next week. Not the derivation, but you should know this. Okay. Well, I'm going to get back to what we started with. So, yeah, this one's getting long enough.